Hi everyone. This video is meant for teachers, and in particular elementary school teachers, to give a little bit more background on solids, liquids, and gases for our states of matter unit. And so maybe you'll pick up something new. Maybe this is all review, but this is intended for you. So when we talk about states of matter, at least in the elementary school level, we tend to talk about the three most common states of matter: our solids, our liquids, and our gases. But we want to remember that there are other states of matter too. So a student might come to you and say, yeah, but what about plasmas? Yes, that's another state of matter. Not one we're going to talk about now, but maybe something that you talk about in middle school or in high school. And if you have a really sharp, clever kid, he might say, yes, but what about Bose-Einstein condensate? That might be something you've never even heard of. And yes, that's another state of matter that they probably won't talk about until maybe high school, but probably college if that's what they want to study. So there are other states of matter than these three most common ones, but these are the ones that we're going to talk about, at least at the elementary school level. So what makes a liquid and a solid, and a gas a gas? Well, it's all about the structure of the things that make it up. So in our solids, we have a structure that the pieces that make it up don't move independently of each other. There's a very famous physicist named Richard Feynman. He likened this to a marching band marching down the street during a parade. And so there are set rows, there are set columns, everybody stays in line with everybody else. There's not this free movement around with all the people. And that's kind of like our solid. Really important to remember, though, that the pieces, the individual particles of the molecules, they're still vibrating, but they're not moving around each other. They're locked in place. Our liquids, well, this is a little bit more free range. Now, thinking about the marching band, perhaps if you've ever seen them on a field during a halftime show, they might scatter. And so the horn section might stay together, and the drum section might stay together, and the woodwinds might stay together. They're still locked together, but there's more of a motion, the pieces moving around each other, and that's like our liquids. One way to think about them is that they flow. Both liquids and gases, they flow, meaning that they can move. Our gases are even more free range, and this would be a complete scatter on the marching field. So all the different instruments are running around doing whatever they want independent of each other. And that is kind of our analogy to our gas. As far as other things that we can think of when we think of a solid or a liquid or a gas, the solid has a definite shape. It has a definite volume. Our liquids, the volume tends to stay pretty fixed. You can actually compress water, for instance, a little bit. Very difficult to do. So we generally say that the volume is fixed. It's the same. But of course, the shape is whatever the container is. So if I pour water into a cylinder, it takes a cylindrical shape. And if I pour it into a pyramidal sort of object, then it will take the pyramidal shape. Gases, on the other hand, take the shape of the object, whatever they're in, just like our liquids. But if I open the door, they will consume whatever space they're given. So they will fill their space. So their volume is not set. You can compress a gas and you can stretch it. Now let's take a look at the process to move from one state of matter to another. So we're going to start at our gas and we're going to make it a liquid. So how do we do that? It condenses. And so that's that process, condensation, condensing. And from our liquid to our solid, well, that's freezing. So it's quite all right to say that any solid is frozen. We tend to superimpose temperature on here, and that can lead down a dangerous path sometimes. So let's think about water. If I talk about solid water, of course I'm talking about ice, and we know that ice is cold. And when we say, ooh, it's frozen, we tend to think of things that are cold. But the metal that makes up your car, or the ceramic mug that you might be holding your coffee in, those are solid too. Those are frozen, but yet they might not be cold. And so it becomes a little bit dangerous when we give examples, just one example like water, that we might lead students down a path of thinking, oh, if it's solid, it's cold. If it's frozen, it's cold. No, if it's solid, it is frozen, and depending on the substance, it might be cold, or it might just be room temperature, or it could in fact be hot. And so we want to give lots of examples of objects moving from one phase to another. And moving from the gas to the solid, that process is called deposition, or to depose. So now what do we call the processes going in the reverse direction? So a solid becoming a liquid, that of course is melting. And we would say anything that becomes a liquid from being a solid has melted. And what about a liquid to a gas? That's called vaporization. Moving from solid down to gas in one step is called sublimation, or to sublime. And an example of this would be if you go out on a snowy day and you see a big mound of snow, maybe early in the morning, and then at night when you come back, that pile of snow is much smaller and there's not a puddle underneath the pile of snow. That snow could have gone from the solid state right to the gaseous state. And so that moves directly to that state and skips the liquid state in between. The last little tidbit for today is about the general rule that as things get colder, they shrink, and when they get warmer, they expand. This comes from something called the kinetic molecular theory of matter, and states of matter is linked to that as well. So that's why I'm talking about it here. In general, when things get cold, they shrink, and when they get hot, they expand. This is why thermometers work. And actually in second grade in our district, we talk about that, why the alcohol in the thermometer goes up and down, because it gets cold and it gets hot. Another example, water. So when water gets hot, it tends to expand in volume, and as it gets colder, it tends to shrink in volume. But water really has this one anomaly in it that's really very interesting. Right when it freezes, as it gets colder, it starts to expand again, and then it starts to shrink. There's a little blip. If I were to take a lot of data points and measure the volume of my water versus its temperature, I would notice that it would steadily decrease as the temperature went down, but then all of a sudden, right after it freezes, it goes up and then goes back down again. This is something that's actually quite remarkable. It has a huge consequence on the Earth. It's not unheard of. It's not unknown why it happens. In fact, it happens because of the way water molecules are constructed. But what's so special about it is this is what ultimately causes bodies of water to freeze from the top down. You might not think that's so special, but actually, if water froze from the bottom up, or if lakes, think about this, froze solid, then we wouldn't have sea life. The life of the animals in the lakes would cease to be. So what happens is, because of the water being a little less dense, because all of a sudden its volume increases, the ice floats and we get ice on top. It basically insulates the water below. Our wildlife can still live throughout the winter, and then in the spring it thaws. This one fact, if this wasn't the case, life on Earth would be radically different, if there would be any life at all. So kind of an interesting little fact about water. We tend to use water in a lot of our examples, and water actually has a lot of little anomalies in it, and it tends to break the rules. If there's one rule breaker out there, water tends to be it, but it's so common we use it for examples all the time.